Welcome back, everybody. This video is going to start our study of gases and pick up with the understanding that if we are to change one property of a gas, and the four properties of a gas are its pressure, its temperature, its volume, and then the number of particles of the gas, that if we are to change one of these properties, that the others will respond as well. And so a fundamental first relationship to understand is the relationship between volume and pressure. And namely that if we are to compress a gas, making sure that the temperature and the number of moles are the same, and compression, that is decreasing the volume, then we're going to have an increase in pressure. And there are pairwise relationships for each of these properties that are really good to know about. And we'll take a look at a few of these, but build more so on how these relationships between the gas particles gets us to an understanding of the ideal gas law and how we can determine one of these properties given that the other three are known, right? With four known properties, if we have three of them, we can calculate the third through this ideal gas law or ideal gas equation of state as it's also sometimes known. So again, this video will discuss how these gas relationships can lead us to the ideal gas equation of state and help to build our understanding of gases in general. So without much more, let's go ahead and get into the video. All right, so we are picking up with our gas relationships. So pressure and volume have an inverse relationship. We've discussed this as Boyle's law. Pressure and temperature have a direct relationship. We'll discuss that one a bit today. Pressure and number of moles have a direct relationship. That is true also, and we will discuss. And temperature and volume have a direct relationship. We discussed this as well as Charles' law, and these two fundamentals, Boyle's law and Charles' law, show us this relationship if we change one parameter of a gas, how a second one responds, given that the others stay constant. So how about pressure and temperature? Well, these are also directly related. If we increase the pressure of a gas, keeping in mind that we're going to maintain a constant number of moles of gas, and we're going to contain a constant number, a constant volume of the gas, right? Fixed V and N. The pressure will increase, right? And so here's a good example. We have a gas in a flask in some water, and when the hot plate is off, it's a cool gas, and we have low pressure. As we start to get warmer, the gas pressure will increase, keeping in mind that no moles are flowing in or out of this gas sample, so N is constant, and it's a glass fixed volume, so the gas has already filled up the volume of this flask, and so therefore volume is increased as well. And once we get to high temperature, we'll have high pressure also. And so one thing that we are able to do with these gas laws is we can combine them all together, right? And so if we have P1 V1 over T1 equals P2 V2 over T2, this is just fine, right? And in this way we can track how perhaps multiple variables are changing and how a variable responds. So here is the following question. I would highly recommend that you pause the video here and work out the question yourself, and we will discuss in just the next slide. All right, hopefully you've been able to come up with an answer to the question. Let's go ahead and take a look at my solution. And so I think with these gas variables, what's really important is to keep everything as organized as possible, right? We have 6 variables that we're dealing with. We're going to find that if we have 5 of them, that we can solve for the 6th. And so identifying which variable we're going to solve for is really, really essential here as well. So I hope you made a table like this. If not, maybe try to lay this out quickly here just to make sure you're keeping your variables organized. And here is what I would place, right? So the volume is 1.25 liters. That volume goes with the 80 degrees C and the 2.75 atmospheres. So here our T1 is 80 degrees Celsius in terms of Kelvin. And our final pressure is going to be 5 atmospheres. And this 458 Kelvin, which again is 185 Celsius converted to Kelvin. And most important here is that we're not mixing up characteristics of the second state with the first state. And also, looking at this problem and seeing, well, this gas is going from one state to a second state. And we'll discuss that a bit more further on here, right? It's starting at this initial 80 degrees Celsius and 2.75 atmospheres. That's state 1, and we've described that as P1, V1, and T1. And the second state is going to have this other PT, pressure temperature condition, that's at 185 Celsius and 5 atmospheres. And the volume at that second condition is what we're solving for. So it's a two-state problem. We've laid out all of our variables, and we can solve for V2, and we obtain that V2 is equal to 0.891 liters. And note here that we have had an increase in temperature, which we would expect to cause the gas to expand, but we've also had an increase in pressure, which would cause the gas to contract. And it seems that that pressure condition is just a little bit more impactful because overall we've had a small contraction of our gas. So when we have PV and T specified for an initial state and mostly for a second state, we can use this combined gas law just like we used Boyle and Charles independently. The final law that we're going to take a look at here is Avogadro's law. So according to this, the volume is proportional to the number of moles. And very importantly, it's proportional for any ideal gas, right? Basically, we're going to say that it doesn't really matter which of these moles we're dealing with, right? Whether it's helium, whether it's ammonia, or whether it's oxygen. All having the same number of moles and the same P and T conditions, we can treat them all the same. We're going to treat them as ideal gas particles. And so Avogadro's law states that V1 over N1 equals V2 over N2, right? If we are to have twice as many moles, it'll have twice the volume. And again, very importantly, regardless of what the type of gas is. And that will really get us to an ideal gas that we're going to discuss here in a minute. But up till, before then, let's discuss this idea that the one mole of gas has a volume of 22.4 liters, right? We call this the standard molar volume. And it's again true for any gas, because we're dealing with ideal gases here, at specifically 0 degrees Celsius and 1 atmosphere. And we call this standard temperature and pressure. So really just driving the point home that it doesn't matter the identity of a gas when we're dealing with these gas problems, right? It will affect the mass of the gas, of course, but when we're dealing with pressure, volume, temperature, and the number of moles, the identity of the gas really doesn't matter. All that matters is how many moles there are. If it's mixed, that doesn't matter either, right? If it's 1 mole of helium compared to a mixture of half a mole of nitrogen and half a mole of helium, that would be just fine. Okay. This really gets us to our ideal gas law, because now we have, through Avogadro's law there, assumed that gases are equivalent, right, and have some semblance of ideality where we can treat them all the same. And so with V2 over N2, let's just lump it into the expression that we showed before with our combined gas law. And now we've actually encompassed all 4 properties, right? This is the 4 characteristics that define a gas. And so we can again say that these are equal to a constant, but because we've actually captured all the different characteristics, this is going to be the same constant all the time. And it's a very special constant in chemistry. It's called R, and this is our ideal gas constant, right? While we have said things like P2 times V2 are constant previously, the value of that constant will depend on how many moles, the temperature, right? Those things can't change, and provided they don't change, we still have a constant. But we haven't been able to actually nail down a single constant that'll be able to be used universally in the same way as this R, right? Again, R will not change, and it has this very characteristic value of 0.08206 liters times atmospheres per mole Kelvin. And definitely note the units of this, right? The denominator moles in Kelvin, that's kind of, should be sort of straightforward by now. N is moles, T must be in Kelvin. But we do have multiple units we can use for pressure and volume. And so if you're going to use this value of R, which I encourage you to do, make sure that you're dealing with pressure and volume in terms of liters and atmospheres. Again, we can say now that PV over NT equals R. And when rearranged, we get this ideal gas law, which is very, very essential in chemistry. PV equals nRT, and this says for a single state, if we have 3 of these characteristics nailed down, we can calculate the third. So basically, if we have a given volume and a given pressure and a given temperature, for example, of a gas sample, we will know the number of moles in that sample because we can solve for N based on R, which is always going to be this number. So we always have that. Okay, so ideal gas, right? I know that many of you may be thinking, we can't really just treat all gases the same, right? They're different. They have different characteristics. And that's definitely true. And there are definitely real gas phenomena that come into play. And we'll discuss that just a little bit towards the end of our gas chapter. But For an ideal gas, we have two key assumptions that end up being pretty good. And the first one is that gas particles are dimensionless. Now, we know this is not exactly true, right? They're protons, neutrons, and electrons. They have matter. But the distance between gas particles is so vast that when we're dealing with volumes and pressures and all of that, the actual volume that's occupied by the atoms or molecules themselves is so negligible, and it doesn't vary that much when we go from one molecule to the next, compared to the vast space between them, of course, that we can say they're dimensionless, right? They're just points in space. And that's assumption one that makes all gases ideal gases. The second is that attractions between the particles are zero, right? No attractions or repulsions. And this, again, we know is not exactly true, but within the context of a gas that are in rapid motion and generally far apart, these attractions are going to be pretty small compared to the kinetic energy of the gas itself, right? So making that second assumption is not so bad either, right? And these assumptions, they really get us like 95% of the way there. And as we study real gases, we'll see that they're all based on this ideal gas basis, right? We basically are going to make adjustments from the ideal gas law to study real gases. And that's true for all real gas models. And so it really is a very important basis for studying gases. And with these two assumptions, what else really varies between molecules, right? Dimensionless, no attraction, and then they're really all the same. So hopefully you're a bit more convinced that gases can be treated as ideal. And so as you get into problems, I would say that a really critical question to ask is, well, there's all these equations, right? Which one should I use? And when we're dealing with these comparative gas laws, note that they all require a change of state, right? We have some initial pressure volume condition, and we're trying to solve for the volume at the second condition, right? So if we have a two-state system or some change in the system, right, change in the gas properties of the system specifically, meaning P, V, T, and N, we want to use these laws on the left, right, because they compare an initial state versus a final state, right, V1 versus V2, and so on. If we only have a single state, right, where we're basically interrogating the state of the gas, we want to use the ideal gas law. And so this would be a case where we are maybe generating a volume of gas, right? And we say, well, we've generated this volume and this temperature, and we can solve for the number of moles based on the stoichiometry, and you may need to calculate the expected pressure, for example. But note that even though there's chemical change occurring, there's only a single gas state that you're basically trying to learn more about. And in that case, we want to use the ideal gas law. Okay, so hopefully this has been a useful introduction to the comparative laws and the ideal gas law, a little bit about ideal gases themselves. Please let me know if you have any feedback, and I will see you soon.